Did you know even the most advanced nation, bridge failure are most common than you think? In America, global leading country in every aspect, over 500 bridge collapsed between 1989 up to 2000, averaging 42 disasters per year. In India, just between 2020 up to 2023, a shocking 32 bridge collapses were reported on the national highway of India. In China, often called the mastermind of megastructure or other construction, 302 highway bridge catastrophe failed from 2000 up to 2014. That is 21 collapse per year. Those numbers prove one thing: no country is away from the bridge failure. And when that happens, the consequences are clearly it's deadly. But what caused those collapse? Poor design, cheap material, natural disaster, or something else? In this video, we will reveal the top 5 main reasons behind bridge failure. Factors that could save life. Stay until the end of this video. Don't forget to like, share, and subscribe for more shocking engineering insights. Your support helps us to expose the truth behind infrastructure disasters. A bridge, the very symbol of connection, can also be the site of disaster. In seconds, life can lost, city can cut off, and question rise. What went wrong? What was wrong? Bridge fell for many reasons. Here are the 5 most common causes. The first one is design problem. Bridge must be carefully engineered to withstand environmental forces such as wind, water, and seismic effect. A failure in design phase either due to miscalculation, outdated engineering knowledge, or inadequate safety factors can lead to the catastrophic result. One of the most iconic examples in this aspect is Tacoma Narrows Bridge in Washington, USA, which collapsed in 1940, just after 4 months of the opening. The design did not adequately account for aerodynamics wind effect. Under sustained wind condition, the bridge began to oscillate violently due to the phenomena which is called aeroelastic flutter, which was not fully understood at the time of the construction. This failure revolutionized the field of wind engineering and leads to a new standard for bridge aerodynamics. The design and construction overview of Tacoma Bridge are: it is a suspension bridge with the main span length 853, and it was the third longest suspension bridge at the time of the construction. The width is only 12 meters, quite narrow for such a long span bridge. And it was aesthetically sleek and economically efficient because it used slender girders instead of more strong truss. And this made this aerodynamically unstable. The other one is poor construction and using of substandard material. Even a well-designed bridge can fail if the construction practice are compromised, using inferior materials, improper curing of the concrete, insufficient reinforcement, or poor for steel structure, for poor welding can also lead to the reducing of the structural integrity. In many developing countries, financial constraints, lack of oversight, or corruption also can lead to the contractor cutting corner. For instance, for the Korogwe Bridge in Tanzania partially collapsed in 2020, reportedly due to the use of low-quality construction material and the lack of skilled labor. Those kind of failure highlight the importance of quality assurance and skill supervision during the construction of the bridge. The third one is lack of maintenance. Bridges are dynamic structures that degrade over time due to wear and exposure of the element to the environment. Without regular inspection and timely maintenance, a small issue like corrosion of the steel components, cracking in the concrete, or blockage of the drainage system can lead to a serious safety threat. The Minneapolis I-35W Bridge in the America collapsed in 2007, killed 30 people and injured 145 people. Investigation revealed that the guest plates used in the bridge were undersized, but ongoing corrosion and lack of proper maintenance significantly contributed to its failure. This failure prompted the USA government to invest billions into the bridge inspection and rehabilitation of the rehabilitation program. This I-35W Bridge failure in Minnesota was a set of tragedy. and highly publicized bridge collapse that significantly influence the bridge inspection and maintenance protocol across the United States of America as well as for in other countries. Bridge overview of this Minnesota I-35 bridge are: it's located Minneapolis in America, and its function is carrying Interstate 35W over the Mississippi River, and it's approximately 508-meter span, and the structure type is deck truss bridge, and the type of truss where the deck is on the top and supporting truss system. What are the national impact? The national impact regarding to the failure of this bridge was policy change and reforms. The collapse triggered a nationwide revolution of the bridge safety. The USA government allocated billions of dollars for the bridge inspection and rehabilitation due to this bridge failure. The states update their inspection procedure, and especially for the bridge with small, similar design and aged component. What are the engineering lessons from this bridge? It emphasized the critical importance of proper design review, highlighted the need for redundancy safety factor, sparking interest in using sensor technology to detect problems before they become disaster. And the other bridge is Morandi Bridge, also other kind of cable-stayed bridge in Genoa in Italy, that tragically failed in 2018, resulting in significant loss of life. Morandi Bridge overview are: the Morandi Bridge is located in Italy, and it's completed in 1967, and it is cable-stayed bridge, and the length of the span is 1.1 meter, 1.1 kilometer, and the main span is 210 meter. The other cause of bridge failure are overloading. Many bridges, particularly older ones, were designed for light load type of bridge. Today, traffic, including heavy loaded truck, mining equipment, and even large crowded during the event, often exceed its original design limit. For example, in India, the Morbi Suspension Bridge, which was collapsed in 2022, which claims over 140 lives, was attributed in the part of the extreme overcrowded during the event. And the bridge had recently reopened after the improvement, but lacked modern load assessment and proper capacity control mechanism, which exceed the load limit, put stress on the joints and bearing and supports, and which lead to the structure fatigue and sudden failure. Actually, it's a very sudden failure. This bridge, the Morbi Suspension Bridge collapse in India was strategic and avoidable disaster that draw international and national attention about the bridge failure mechanisms. So this bridge is called the swinging bridge because of this nature, its nature of suspension, and which is located as mentioned, located on the Morbi, India, and this bridge crossed Machu River, and this bridge was originally constructed by 1877 by British, and it was reconstructed again by the Indians again. And the bridge type of this one is a pedestrian bridge. It's used for the pedestrian only, and the total length is 233 meter, and the width is only 1.2 meter. And as compared to the width, as compared to the span, the width is very small. The other one is a natural disaster, and natural events such as a flood, earthquake, tsunami, or landslide can severely damage or destroy bridge, especially if they were not designed to withstand such force. In Ethiopia, bridge foundations are often vulnerable to scoring and erosion of the soil around the pier due to the fast moving of the flood waters, and intense rainfall and poor hydraulic design lead to the foundation failure. Those events highlighted the need of the detailed investigation, especially geotechnical investigation, for the bridge design and the construction of the bridge, which can withstand different clientele. Earthquake-induced bridge failure. House bridges that are not designed to withstand seismic load can experience severe shocking during the earthquake, which leads to the foundation failure, and pier or column also crack, or shear deck dislodge from the support, also one of the cause of this failure. And the main example and the big example for this earthquake is Kobe. the Kobe earthquake, which was happened on 1995 in Japan, and it affects a lot of things. And the magnitude was actually, it was great, 6.9, magnitude was 6.9, and entire section of the elevated highway was washed out and disaster, and over 6,000 people also died in this accident. And the main reason for structure the bridge failure was inadequate seismic detail in the pier and lack of the reinforcement as well. The other one is flood and score induced failure. Flood also caused a big failure for the bridge, and during the heavy flood or water flow rapidly around the bridge piers, score may happen around the riverbed and remove the supporting soil. If the foundation become unsupported, the bridge definitely will collapse. It's clear. And the main example for this such kind of failure is I-9 bridge, which is located in the United States of America, New York, and it was 1987. And the main cause was spring water, flood water scored the riverbed, and resulting the pier lost its support, and 80-meter section of the bridge was collapsed immediately. And during this event, 8 people were dead. No proper score protection around the pier can cause such kind of failure as well. So the third one is hurricane and wind-induced bridge failure. So when it comes to the hurricane, high winds or storm surge and wave impact during the hurricane or cyclone can lift the bridge deck off the support, and especially the low layering of or coastal bridge. For example, for this kind of failure is Bay St. Louis Bridge, Mississippi, which is located in America. Also, the bridge that was failed by this hurricane, and the bridge deck segment lifted and washed out due to this hurricane. And the main reason for this one is the wind-driven storm surge undermine and dislocate deck segment. So that was the main reason. The other one is the landslide induced bridge failure. So the landslide can also undermine bridge foundation, so damage the pier or block river, leading to the back flooding or pressure against the bridge, which also cause the destruction of the bridge. The other one is the tsunami related bridge failure. Tsunami also bring massive water pressure and floating debris, which can stick the bridge pier or the supporting component and cause disaster. The best example for this one is Great East Japan earthquake tsunami, which caused by this earthquake and the tsunami is very disaster. Several coastal bridges were destroyed or severe damage was happened due to this one. The damage include washed out of the pier and the score embankment, and that was a big disaster. Generally, bridges do not just fail immediately. They give us signs. If we are willing to look, regular inspection, update design code, and responsible for the construction can prevent a lot of disasters that happen on the bridge. As an engineer and citizen, we must advocate for safety, quality, and innovation in infrastructure, especially that of the bridge. Which bridge failure shocked you at the most? Let us know in the comment section. If you found this video helpful, give us a like and subscribe this channel and share this video for anyone who is interested in engineering and infrastructure.